Yes. So, okay, good. Welcome everybody to attend the Coastal Oceanography and Inland Water session. This is part 2. And my name is Guoqi Han from Fisheries and Oceans Canada. So before introducing first speaker, just some simple rules. Each speaker has 15 minutes in total. So in 10 minutes, I will give a warning reminder, and you should finish, in 2 minutes, and we will have some questions and answers. And for audience, please put your question into question and answer tag, and the speaker will read out your questions and answer the questions. Okay, so now I would like to introduce Kyoko Ohashi. She's going to talk about quantifying hydrodynamic connectivity between MPAs over the Scotian Shelf. Kyoko?
Yes, thank you. I hope you can hear me.
Yes, I can hear and see your slide.
Great. Thank you, Kochi. My name is Kyoko Ohashi from Dalhousie, and this is work that I have been doing with Jing Shang as my supervisor. Bruce Hatcher at Cape Breton University is the other PI, and Bo Yang helped us with the ocean circulation work when he was doing a sabbatical in our department. I think many of us here have heard of the 30 by 30 initiative, in which countries around the world commit to protecting 30% of its marine and terrestrial spaces by 2030. Canada is part of this initiative, and marine protected areas will be a key part of this effort. So the goal of our work is to use ocean circulation and particle tracking models to address 3 questions. One is, how are existing marine protected areas interconnected? The second is, how will this connectivity change under the future climate? And given our estimated answers to the first 2 questions, the third question will be, where are the best places for new MPAs? So in today's talk, I will address the first question and show how 2 MPAs, one in the Gulf of St. Lawrence and the other in Kappa Strait, act as source areas of passive particles for different parts of the Scotian Shelf, including another existing MPA on the Scotian Shelf. And I will also present some very preliminary work addressing the second question using connectivity matrices. So one moment. So our study area, the waters of Atlantic Canada, have been heavily studied, and that includes applications of Lagrangian particle tracking. And many of those studies have focused on certain species, such as Calanus copepods in works by DFO scientists, and Atlantic sturgeon and salmon in work that our group has done as part of the Ocean Tracking Network. There have also been work done focusing on existing or proposed MPAs, such as Shiliang Shan and co-workers' work for the Gully MPA, as well as Maëla's work for the Eastern Shore Islands area of interest. And our goal is a little bit different in that we want to characterize a large region. So our approach is somewhat similar to the work by Zhong et al., in which they use particle tracking to identify areas of high retention on the Scotian Shelf. And they also found correlation between interannual variability of that retention index and cod abundance on the shelf. So the first part of our methodology is the ocean circulation model. This is the domain. We are coupling the circulation model ROMS to the sea ice model size. The horizontal grid resolution is between 6 and 7 kilometers in our study area. ROMS uses terrain falling layers, and the lateral boundary input of the ocean and ice states are from the GLORIS reanalysis The atmospheric input is from the ERA 5 reanalysis. We also specify tides at the lateral boundaries, as well as freshwater input from rivers and freshwater input from melting glaciers. And to counteract model drift and bias, we use the semi-prognostic method and spectral nudging. The simulation was initialized on September of 2013, and we will be using model results from 2015 to 2018. And we just submitted a manuscript showing that the model performance is reasonable throughout the model domain. And the second part of our methodology is the particle tracking model. We are using an open source program called ROMSPath, which is designed for use with ROMS output. We are using time invariant seasonal mean simulated currents from the 4-year period, 2015 to 2018. The particles are passive, so they are moved around just by the currents. They do not swim, and so they can be seen as representing larvae. And we add horizontal random walk with a diffusivity of 10 meters squared per second. There is no vertical random walk. And we have 2 sets of experiments. In one, I release particles from this MPA called Banque des Américains in the Gulf of St. Lawrence. And then in the other set of experiments, I release particles from the St. Anne's Bank MPA of Cape Breton. And in the next few slides, I will show the 4-year aggregates of particle distributions for each season. So in the first set of slides, I'm showing the results for the St. Anne's Bank. So here I'm showing the 4-year aggregates of the seasonal mean particle distributions. So we can see that there is a lot of seasonal variability. And if we look at the summer, there is a relatively high concentration of particles near the Sable Gully, which is the location of the first MPA in this region. And we can also see that there are not very many particles along the Nova Scotia coast, which is something I'll come back to later. And we suspect that it's because of this gap between the Cape Breton coast and the western edge of this MPA. So that was the St. Anne's Bank. And here I'm showing the similar plots for the Banque des Américains MPA. So again, we see a lot of seasonal variability, and the particles reach the Scotian Shelf more rapidly in the winter and the fall. And we can also see that this Banque des Américains MPA also acts as a source area for the St. Anne's Bank MPA. And I should have mentioned these are particle distributions 60 days after release. And now I'm showing the same thing 90 days after release. And we can see that in these cases, there are more particles traveling near or along the Nova Scotia coast than in the cases where the particles were released from the St. Anne's Bank MPA. So in this part, I was showing the simulated connectivity among existing MPAs. But the ultimate goal of this project is to figure out good places to have future MPAs. So what I did here is to divide our study area into 78 squares. Each square consists of 10 by 10 model grid boxes. And in each of these squares, I released 40,000 particles, again near the surface, and I tracked them for 90 days. And because this work has just started, I only have results for winter of 2015. So here I'm summarizing the results of those 78 experiments in terms of connectivity matrices. So in each matrix, the y-axis represents indices of the source areas, and the y-axis represents indices of the sink areas. And I have a matrix for 1, 2, and 3 months after the particles were released, and the shadings represent the percentage of particles released from each area that end up in each sink area. So for example, if I look at source area number 60, there are a relatively large number of particles ending up in area number 40. So if we go over to the map, I can see that that means that particles released in the center part of the Gulf tend to end up in the offshore part of the eastern end of the Scotian Shelf. And also, when we look at this matrix after 30 days, the particles tend to end up close, or the shaded areas are close to the 1-to-1 line, meaning the particles are still close to their source areas. Whereas after 2 months and 3 months, 2 patches emerge, and one represents the area from the Gulf of St. Lawrence to the to most of the Scotian Shelf, and then the smaller patch represents the area from the southwestern Scotian Shelf to the Gulf of Maine. So then, so these were preliminary results, but the conclusions for the first part is that our experiments suggest that the St. Anne's Bank MPA acts as a source of passive particles in the summer on timescales of about 60 days for the Gully MPA. And the Bank des Americains MPA in the Gulf acts as a source area for the St. Anne's Bank MPA, and for inshore areas of the Scotian Shelf on timescales of 2 to 3 months, especially in fall and winter. And our early results for the region-wide experiments suggest that the Gulf of St. Lawrence to the north and the northeastern Scotian Shelf and the southwestern Scotian Shelf and the Gulf of Maine are distinct regions for passive movement. So in the future, we would like to expand our experiments, the second part of our experiments, to all the seasons and years. Also add experiments where particles are released near the seabed. We also want to add swimming behaviors, and we need to also repeat all of our work for ocean circulation states that represent the future climate. And that's all. Thank you very much.
Oh, thank you so much, Kyoko. Yeah, it's just, that's very good. Interesting talk. And so do we have any questions or comments? And please put into your question and answer tag. Kyoko, can you see any questions in the question and answer tag? So here there's one question. Can the particles move vertically?
Sorry, they are able to move vertically due to the simulated currents, but we are not adding any vertical random walk. So all the vertical movements right now are due to the simulated currents.
Okay, thanks, Kyoko. And I also have a question. So, yeah, so you do have a horizontal random. Okay, you added a horizontal diffusivity for random walk.
Yes.
So how do you consider when you choose 10 meters squared per second, what's the rationale behind that choice? Do you think if you change that would be how sensitive? Or have you done the sensitivity?
I think yes, we did some sensitivity studies, so it's rather ad hoc, and so we do need to add the random walk because our grid size is several kilometers on each side, and we just try different values of the diffusivity until we could see that the patches are somewhat spread out. Because if we do not add any random walk, then we have a very tight clump, a tight patch of particles. So we increase the diffusivity until there is some spread, but and it's somewhat subjective in terms of where we stop increasing the diffusivity. And we stopped at what we felt was a reasonable value. So it is somewhat subjective. And
Thank you. Let me see if there's more questions. Let me see. Yeah, have a nice day. Okay. Yeah, there's a second question. So,
Yes.
hi, Kyoko, nice talk. Do you think
you.
including tides would give a different answer?
Yes, so tides are included in the ocean circulation simulation, but we are using seasonal mean currents. So ideally, we would save hourly currents and so that we can more accurately simulate the movements of the passive particles. And as Susan mentioned earlier, tidal movements are not symmetrical between flood and ebb, so there would be a net movement. So that will affect our results. So the ideal thing would be to save hourly currents using the tides. So there is information that we are losing by using seasonal mean currents. Yes.
Thank you, Kyoko.
Thank you.
Okay. So the next presentation is given by Qiantong Pei. His presentation is on storm-induced hydrodynamic change and wave current interaction, also in the Southeastern Atlantic Canadian Shelf.
Can you see my PowerPoint?
Not yet.
Oh,
Maybe it's, let me see.
okay. How about now?
Now, yes. Good.
Oh. Hello, everyone. I'm Albert Pei, a PhD student in Dalhousie University. In this presentation, I will talk about hydrodynamical availability and wave current interaction during Hurricane Fiona. This presentation includes introduction, model setup and validation, model results, and wave current interaction during Hurricane Fiona. Hurricane Fiona is one of the most damaging storms in Atlantic Canada on record, with a combined damage of over 800 million Canadian dollar. Fiona made landfall over southeastern Nova Scotia with peak winds of 150 km per hour and a minimum atmospheric pressure of 931 millibar in late September 2022. The scientific question to be addressed is related to the ocean response to Hurricane Fiona and the associated wave current interaction. The main objective of this study is using a coupled wave circulation model to investigate the hydrodynamic availability and wave current interaction during this storm. The study region includes the Southeastern Canadian Shelf and adjacent deep ocean waters. The model couples the regional ocean modeling system and simulating a wave nearshore model and has a horizontal resolution of 1/12 degree. These circulation and wave models are used widely in previous oceanographic studies. 3 numerical runs are involved in the current study: the fully coupled run, which is the realistic simulation; the circulation-only run, which only use the ocean model; the wave-only run, which only use the wave model. This model result.
Can your slides are not advancing.
Okay.
I don't know if, oh yes, now, yeah.
Okay. There are 3 model runs, including the fully coupled run, the circulation-only run, and the wave-only run. The circulation-only run use only the ocean model, and the wave-only run only use the wave model. the red panel shows the animation of a surface temperature and the currents during Hurricane Fiona. The red dashed line shows the storm track, and for the red panel, it shows the significant wave height in meters and the surface current. As we can see from this animation, during Hurricane Fiona, there is a large surface current biased to the right of the storm track. Around the storm track, the large current are mostly the wind-driven current, and in the wake of the storm track, the large current are mostly the near inertial currents induced by the storm. As we can see from the animation that there is a noticeable SST cooling over the coastal and shelf waters there is a large significant wave height biased to the right of the storm track. We also calculate the near inertial currents induced by the Hurricane Fiona. As we can see, the near inertial currents at the sea surface is large and biased to the right of the storm track. However, over the coastal and shelf waters, the near inertial currents are much smaller. This is probably due to the bottom bathymetry and a bottom fraction, and we are still identifying the related physical mechanisms. Here is since the damage of the storm is due mainly to the flooding and coastal erosion, which is closely related to the sea level variation and the wave heights. We validate our model versus the tidal gauge station observations. For this comparison, we only look at the fully coupled results, which is shown by the black line, and the observation shown in red line. In the blue box, there is the blue box labels the period of Hurricane Fiona. As we can see that our model results do a satisfactory scale in simulating the sea levels, and these small gamma square values are comparable with their counterparts from previous study over the same region, but for different storms. We also compare our model results versus the satellite remote sensing data. The left panel shows the remote sensing data, and the middle panel shows the model results, and the right panel shows the scatter plot between remote sensing data and the observations. The lower panels are showing the same thing, but for after the storm. From this statistical error indices, which are correlation coefficient, gamma square values, relative bias, and scatter indices, we think our model has satisfactory scale to reproduce the SST before and after the storm. This animation shows the comparison of a surface current generated by fully coupled run, which is shown by the blue arrows, and the wave current interaction on the surface current, which is shown by the red arrows. As we can see from this animation that the wave current interaction generate anticyclonic modulation of surface currents around the storm and biased to the right of the storm track. The wave current interaction modulates the surface current associated with fronts and gears, as shown by the persistent red arrows over the Gulf Stream and the Northwest Atlantic current. And also, the wave current interaction noticeably reduced the magnitude of tidal current over the Gulf of Maine, as we can see the comparison between the red and blue arrows. Here, we use the fully coupled model results minus the circulation-only model results to quantify the impact of wave current action on surface current, which is shown by the vector, and sea surface temperature, which is shown by the color image. As we can see from this animation, the wave current interaction enhance the SST cooling over the coastal and shelf waters, over the Scotian Shelf and Newfoundland and Labrador Shelf by up to 2.6 Celsius degree. And the wave current interaction also modulates thermal fronts and enhance the vertical mixing over the coastal and shelf waters through the wave dissipation as a main reason why there is enhanced SST cooling over coastal and shelf waters.
2 minutes.
Next, we look at
2 minutes.
Thank you. Next, we look at the effect of wave current interaction on the significant wave height. The left panel shows the maximum significant wave height from 1 day before the Hurricane Fiona to 1 day after the Hurricane Fiona. This period is chosen to include the impact of a swell. As we can see from the left panel, the largest significant wave height is up to 21 meters over the deep waters and up to 16 meters near the Cape Sable Island. We calculate the difference between fully coupled results and wave-only results normalized by the wave-only run in terms of the maximum significant wave height. And by this result, we can see that the wave current interaction reduce the maximum significant wave height by up to 8% over the area with largest significant wave height. Here is the summary of the current study. In the future study, we will quantify the terms associated with wave-induced forcing and the non-conservation wave-induced processes. And also we will make a fine scale model on the extreme current and waves over the Scotian Shelf during Hurricane Fiona. And that's all my presentation. I will be happy to answer any questions.
Yep. Thank you, Alberta, for nice presentation. And we have questions. Do we have questions, comments? Please type into question and answer tag. And for those on Zoom, you can also directly ask a question.
I don't think there is any question.
Yeah, don't you see any? Let me check.
Yeah.
Okay. So maybe I have a quick question. So what atmospheric phasing do you use?
Oh, the atmospheric forcing. I got the atmospheric forcing from Dr. Peng Cheng Wang. These data are from the DFO. They have the high resolution atmospheric forcing that is in 15 kilometers.
Oh, okay. So do you this time don't use any kind of like a hurricane model to modify those wind fields?
Yes, because in his study, some other study on Hurricane Fiona, they use their data product directly. So I do the same thing.
Okay. Yeah, that's
yeah,
good. But you're getting reasonable good results. Yeah, that's good. Okay, thank you.
Yeah, thank you.
Okay. So now we move on. And the next presentation is given by Rick Daniels. And the topic is a hydrological model and calibration and simulation for Eastern Canadian watersheds.
Thanks, Guoqi. Can you see the slide?
Yes.
Started in presentation mode. Okay,
good. Yeah.
So Joel and Will and I thank you for the chance to talk a little bit about an update to a seminar from last year at CMOS, in which we start to use neural networks. So I'm going to motivate our calibration to both processes and to data in this talk, and the data calibration is the neural network part. And try to motivate with respect to neural networks an adjustment of CMIP forcing of wharf hydro, the hydrologic model, directly to station observations. So it's a little bit experimental, but it seems to verify when we compare to ERA5 reanalysis. And just a reminder that we're considering, or we have considered, topographic, atmospheric, and hydrologic representations in this work, but I won't be talking about the topographic part. That was last year. So the references are, I'll get to the references in a second. First, just let me summarize the context of this study. We're looking at long time scales. So as global temperature rises, precipitation, permafrost, these are variables that are changing. They have trends, and the specific component of coupled modeling simulations that we're looking at here is in an uncoupled context, is the cold season river discharge increasing and an earlier peak discharge as well. This is something that seems to be occurring and is expected to continue to occur. In hydrology, it's worth noting that there is a good healthy conversation going on about how to calibrate, what processes or data do we calibrate to. And typically in geophysics, we calibrate to the process, or we calibrate the models with the goal of improving the models. But sometimes we ask if, in hydrology anyway, if the models that we're using are agile enough, scalable, for example. And in that context, sometimes it's interesting to calibrate to the data, the emergent data, so the coupled data historically. If we were to do that, would we also not want to do the calibration to the process as well, is I guess our question here. These may be, in fact, parallel activities. So what's our data model? Or in other words, what are our representations, and what are the references that we're using to adjust the model, to calibrate the model? And if we were to write down the model, it would look probably as simple as this mathematical equation here, where the reference is truth, and the uncalibrated representations can be calibrated linearly. I think in Diane Trenberth's work, that's effectively what they're doing when they're calibrating from high stations to the coast. In that process on the right, I'm just showing how we treat the CMIP output, how we use it to force the model. We generally may not use it as well as we should. We may not use the model as well as we should, tune the model as well as we should, and we may not use the input, the forcing, as well as we should as well. So in this calibration process, we want to try and become more precise in our outputs, because they'll be handed off to the ocean modelers in the end. One of the things we do, rightly or wrongly, is calibrate the forcing data, and we do that over the historical period. We'd make small adjustments, seasonal adjustments, for example. That's fairly typical in hydrology. We're doing a very simple linear adjustment, but one that has a daily variation over the course of the year. And in terms of calibrating to the process, we're using a parameter estimation tool, which is automatic. So we have a small simulation period that we'd like to improve the simulation of. We use a relatively linear forcing of the model parameters to get the observations, to mimic the observations within the physical constraints of the parameters, the expected physical constraints of the parameters. And as a result, if we iterate on the cost function, we can see improvements in standard parameters of performance for hydrology models, the Nash-Sutcliffe efficiency, Pearson correlation, root mean square, and bias, root mean square difference and bias. We're doing this iterative process for an entire domain, but we're comparing specifically to these 25 locations where we have station observations. And we're only looking at a couple of some small subset of the parameters in the model. Interestingly, if we go outside that process of calibrating to the process in the model, we can get rather large improvements when we post-process the output of the model using a simple neural network like the one shown here. It's practically one of the simplest possible. I'll get to the details in a sec, but basically what we're using this neural network to do is just smooth out the peaks, the hydro peaks, if you want to call them. There are peaks in the data. And so, for example, for this watershed, where the station is down here on the lower right, we see in the raw data, so the yellow peaks are kind of on the large side over the course of a year or two or three. And we'd like to smooth them out in the monthly or the annual mean daily time series, but also in the daily time series. So we use this first neural network to do that. But we could go further, I suppose, and train to better target individual watersheds. And so we have another neural network, which is a little bit more elaborate. But it's designed to focus on individual watersheds. And we can fairly easily compare the inputs, which is from WRF Hydro, and the outputs, which are from the station data, and tune that model up, because the ERA5 forcing of WRF is synoptically corresponding to the output to the station observations of stream flow. So that's an easier task, but we can illustrate that it works, because in the say if we were to use so-called good stations as our metric of performance, then these would be monthly differences that are less than 15% between model and observation, and Nash-Sutcliffe efficiency of greater than 0.5. When we compare raw to the neural network in the red boxes, we improve the performance in terms of number of good stations. We're doing a split data set comparison. So we're not training on the same data that we're evaluating on. If we add this targeted neural network training for each of the individual 153 watersheds and stations, we can significantly improve the match between the model and observations. The problem with this process, this training, of course, is that CMIP model forcing won't be synoptically correspond with the station observations. So how do we train a neural network there? But luckily, there has been work on comparing, making relationships where there's no strict collocation between the data. We simply reorder the data so that the strong stream flow from the model is matched with the strong stream flow from the observations, and we do that for the daily input to the second neural network. And we don't reorient or resort any of the data for monthly and annual average. So this is a seasonal calibration of the neural network, but it gives us these sorts of results, or these sorts of opportunities, which is to improve the lower lighter colors to better match the black observations. And that's what the purple lines are showing for this large regulated St. Lawrence watershed. Basically, the model is under predicting the stream flow, and we need to shift it upwards. And the end result is, here, I'll show you another one. The end result for Churchill is not just
2 minutes, Rick.
Okay. It's not just that the shift is possible, but also that the scatter in the scatter is reduced as well. So it's a little bit more precise. So we can Diane Trenberth has done a linear calibration up to the coast, and we can do a nonlinear calibration. And again, we can verify that the stations improve. And this is the final result, I guess, for all the poor points around the Eastern Canadian basin. The raw data is too noisy, and the first neural network smooths too much. The second one seems to collapse down to a reasonable result. So that's, again, our representations and references. And later in the conference, hopefully, if I get a chance, I'll talk a little bit about data modeling and process modeling if I can. Thanks.
Thank you very much, Rick. So, questions or comments? Please put your questions into the question and answer tag, or for those in Zoom, you can directly ask a question.
Yeah, I guess a comment I could make is that it's a little bit more difficult to ask questions when you have to filter it through the chat, but that's our format this year.
Yeah, that's right. Let's see. You're able to see, or I have a check, you know, to see if there are any questions for you. Okay.
It's okay. Yeah, let's go on.
Yeah, no question. So yeah, very good. Thank you so much, Rick, for the interesting talk. And yeah, well, let's move on. So the next speaker is going to talk. Next speaker is Maëla Le Ménec. I'm sorry if I pronounce that. Hopefully it's close.
Okay.
And so she's going to talk about estimating uncertainties for predicted drift trajectories in the estuary and the Gulf of St. Lawrence. Yeah, please go ahead.
Thanks. So good evening, everyone. I'm Maëla Le Ménec, and I'm a master student à l'Institut des Sciences de la Mer de Rimouski. My supervisor are Cédric Chavannes and Danny Dumont. And today I will present my results on my research on estimating uncertainties of predict surface drifter trajectories in the estuary and Gulf of St. Lawrence in Quebec. So my research is a part of the T-Rex mission, which took place in the estuary on the marine vessel Coriolis 2 in September 2020. During this mission, a dye was released to simulate an oil spill. And for my part, I focus on the data from the drifter. You can see some on the picture, it's a white small point. So when I study the drift, of course, for oil spill response, as I mentioned with the dye, and also for search and rescue at people at sea. And that also include the drift of storm debris or plastic debris. So drift model already exists, but our goal is to identify and improve the areas of uncertainty in this prediction. So as illustrated in the diagram, from an initial point, we simulate a lot of possible trajectories represented in gray. And with all these trajectories, we determine a search area, I represent in blue, and we validate the area with the real drift trajectory in red. So the drift is calculated with this equation, x representing the position of the drifter. And in the right-hand side, you have two velocities to calculate it. First, the advective velocity, which corresponds to all the predict drift, which include the current, the wind, and the stock drift. Stock drift is the drift due to the wave. And the second velocity, it's diffusive velocity. So that corresponds to all the unpredictable drifts, like the error of the model and all the unresolved processes of the ocean. So to achieve this, we use the data drifter, like I said, from the T-Rex mission. I have two types of drifter, undrugged drifter and drugged drifter. And you can see here all their trajectories in the St. Lawrence. They have been launched near Rimouski with this multi-scale pattern. So at each point, two buoys have been launched and spaced apart by 30 meters, 300 meters, 3 kilometers, and 30 kilometers. The wind, the current, and the stock drift are derived from a numerical model with 1 hour resolution and 2.5 kilometers, and 500 for the wave, 500 meters for the wave model. So now let's talk about my methodology. For now, most of the operational model use the first equation here of for the advective velocity, with the current at the depth of the first cellule of the numerical model and just the wind, so that don't include the stock drift. So my advective velocity improved model, I extrapolate the current at the surface or at the depth of the drugged of my drifters, and I had the stock drift and coefficient to all of my 3 parameters. So to determine the coefficient, I use this optimization function who use the velocity of the real drifter, and I obtain this coefficient. So here I just present to you the result with the drifter with a drugged because of the time. So here are the coefficient for the drugged drifter. And I have put 2 scatter plots. The first one is the velocity of the current numerical model compared to the drifter velocity. And as you can see, the correlation is not high. And the second present to you the optimized velocity of the advective velocity compared to the drift velocity. So we can see a little improve, but it's not significant. For the diffusive part, we have used 2 stochastic models, the random wall model with a diffusive coefficient and a random increment from this Gaussian. So it's a random impulse add to the advective velocity. And for the random flight, it's also a random impulse, but we add to it a memory of the previous step of the drifter. So to determine the diffusion coefficient, we have calculated all the autocovariance of the difference between advective velocity and the drifter velocity. You can see them in gray, and we have calculated the mean covariance to obtain at the 0 lag the variance of the coefficient. And after that, we fit an exponential on it to obtain the decorrelation scale of the coefficient, the diffusion coefficient. So all these parameters together give me my drift model, and we obtain this type of results. So here you have a simulation who use a random walk and a simulation who use a random flight. The red line, it's the real trajectory of one drifter. In gray, you have some of the simulated trajectory, just 10, but we simulated 1,000 trajectories each time. So, and the 3 areas are the area after 6 hours of simulation, 12 hours of simulation, and 24 hours of simulation. So this area are 95% of the simulated trajectories. And as you can see in this case, the area are validated by the real drifter. But that happens that doesn't work, like in this case, where the trajectory of the drifter don't validate my area. So here, a graph who present to you the percentage of area validated by the drifter. And as you can see, we don't attain 95% of success, and that decreases a lot with the time of simulation. So we try to see if we are close to the reality with our area. And the first graph is the distance between search area and the true trajectory. So that increases also with the time, and it's high. It's a very high result. And you have also the diameter of the search area in the simulation time. And as you can see, also the area increase a lot with time. So to achieve the 95% of success, we try to multiply the different coefficient by 2. So for the 3-hour simulation, we obtain our success, but that decrease a lot also. And the area, if you look at the diagram here, it's very bigger. So the points are for the 1K, the diffusion, the normal diffusion, and the stars are for the the diffusion multiplied by 2. So you can see the area is really bigger, and you have an example here too. So as you can see, the difference between the stochastic model are not significant, and we don't attain our confidence level. So we try to found the explanation of that. So here you have arrow in blue who represent the current from the numerical model, and some trajectories of drifter. And the current are the numerical model current as at the time of the last step of the buoys. So we see two eddies in the current, and if we look to the drifter, this seems to take an eddies between the eddies simulated by the numerical model. So it seems that the numerical model don't put at the right place the eddies in the estuary. Also, if we look at the power spectrum of the drifter velocity and the advective velocity, we see that there are a real difference of energy, and that's correlated with our scatter plot before. So the numerical model decrease a lot the current that affects the drifter. So to conclude, the current numerical model cannot be used for real purpose, such as session rescue areas for operation. But there is real need of data assimilation in forecasting model. In the submarines, SWOT satellite will use altimetry start to pass at low frequency, but we can imagine future satellites like this. However, the most interesting development are on the estuary coast. Some high-frequency radar are there, and they can be used for assimilation, but also they can be used in real time for intervention. So thank you for listening, and ask a question if you have.
Thank you very much. Nice presentation. Yeah. Okay. So let's, if you have any questions or comments, please put them into the question and answer tag. Okay. Okay, so in the tag, yeah, are you able to see it?
Yes,
Okay,
the first
fine.
question are the circulation and wave model curve are then run separately. So the wave model is coupled with the current model, but the current model don't use the wave of the wave model. The headies in the the second question is for how long are those headies stable in the real world? So the numerical model simulates that the eddies stay during like 4 days, and I don't know really how long they stay in the real world, but the numerical model predicts that. The third question is, have you compared with trajectories computed with current from high frequency radar? So no, the TRIX mission want to do it, but the HF radar don't record data at this time because they were too low in wind, and they function if the wind are with a small wave, so they don't give us data at this time.
Okay. Thank you very much, Maëla.
Thanks.
And so we will now move on to our next presentation given by Dave Greenberg, and he's going to talk about models for aquaculture in Nova Scotia and Southwest New Brunswick. Dave.
Thank you, Guoqi. Can you hear me?
Yes, I can.
Okay. Okay. I think. Okay. Are you seeing the presentation properly?
Yes, your presentation is up. Yes.
Okay.
Perfect.
Very good.
Okay.
Okay. So this is going to be a little bit of a history lesson. A little bit of status report and sort of a little bit of what we're going to be doing in the future. Now, many people have contributed to what I'm going to present in this talk, and I haven't listed them just because it'd probably take about 3 extra slides, and I've already got about 10 too many. So anyway, I'm going to try to rush through this. I will try to drop a few names as I go through it all. We start off. Whoop, I did not go to presentation mode. Oh, heavens. Are you? I'm sorry. I've got it. It's not coming through in presentation mode, is it? Okay. Hopefully everybody's seeing everything. I don't know how you get in touch with me if you don't. Hopefully you can find some way.
Dave, no, we don't see a presentation anymore.
Oh, you don't? Okay. Are you seeing the no side? Oh, okay. Just
No,
yeah.
no.
Okay. Were you seeing the full screen before?
I think I thought it was for screen, so that's why I didn't say anything, I think.
Oh, okay.
Yeah.
We'll try again. Okay. Okay. Well, are you seeing anything now, Guoqi?
Yeah, I think it's for screen, yeah.
Okay. I cannot see anything, so I don't know where my
Oh.
screen is.
Yeah, your screen is was ice cube or something.
Yeah, that's not the presentation.
Not the presentation.
Okay, there we are. Okay.
Yeah.
Okay, is
Good.
everything there?
It's,
Okay, good.
Yeah, great.
Sorry, now we have to go even faster. Okay, so I've started out working with Fred Page and the crew in St. Andrews, and the model we were using was called Quadi, just coincidentally, not because of with the application. We're doing lots of neat things with it, but primarily we started looking at drifters and did a quick look at what's happening here in this area in the southwest New Brunswick and the entrance to Passamaquoddy Bay. You start with a bunch of drifters and you take a look at them, what happens at low tide. Well, in low tide, things are going to rush into the bay on the right here. And after one tidal cycle later, they're pretty much in the same place, and that goes for all 3 levels, surface, middle, and bottom. After a couple of tidal cycles, some of them have broken away and found their way into the Latite Passage, very high currents that are there and have broken away. The very different picture happens when you start at high tide. They quickly just find their way into Latite Passage, and from then on, they don't know where they came from, but some of them, they do hang together and stay in a coherent group. Now, why is that the particle tracking useful? Well, because of the bay management areas, they try to figure out how do you figure out which farms you put together in one group so that they're all managed collectively and they're not, if they're going to infect each other, that means they have to disinfect at the same time and do their lay fallow at the same time so that there's not a constant infectants and sea lice bothering them. So the classic way was just, okay, 5-kilometer radius, and I think that came from Scotland or Norway, and say, okay, stay that distance away. Well, that's not related to the physics, but if we look at just the M2 and the Quadi program we were using was just looked at M2, was 3-dimensional, but barotropical, uniform density. And we look at how does that what happens if we start particle tracking around in those areas, and we can see an envelope of over one tidal cycle. That gives us some measure of where things are going. And if you use your own favorite GIS program, you can start to put envelopes around these things and say, okay, which farms should go where and which are compatible and which don't overlap, and yeah, you end up with that sort of picture. We then another thing you can do with particles is done with Keith Thompson and crew, where they use the Markov chain approach, where divide everything up into areas, and you can say, well, if we know how things are happening in one tidal cycle, maybe we can predict what's going to happen in 10 tidal cycles or later on. So we'll see that this becomes useful later on. But here's a picture of what happens if we do it with one tidal cycle and 10 tidal cycles. Now, observed is misnamed here. That really should just be the 10 tidal cycle picture, but we try to predict what's happening in 10 tidal cycles by looking at the first and say, how is farm 1 connected to farm 2, and how does farm 2 connected to farm 1 and farm 3, and predict, okay, what does that tell us about where things are going? Well, we end up with a picture that looks pretty close, better than order of magnitude, and certainly relatively correct. So it's going to give us some useful results. And we say, what particles stay in the same farm? Well, yep, same sort of picture, and a pretty close picture as well as to which particles are moving from one farm to another farm. And here we're looking at different farms going into farm 14 or into area 14. And again, we're getting a very decent picture of what's going on, but much better than just order of magnitude. But that is going to be useful when we try to get into the more complex predictions. Now, there's other ways of doing particles. There's this is from work from Susan Egg did. With FECOM, and that is if you can do it with a sort of a dye where you're tracking concentration, or you can use the particles. Now, one is with high resolution, one is with low resolution. We can see we get a better definition with the higher resolution, which is on the right. Starting at the same point, look at again after a period of time, well, 180 minutes later here. And a couple of things a little bit worrying. One is look at the diffusion that we're getting in the coarse model, not quite so much in the fine grid model. And it's not even centered in the same sort of area. And with the finer model, we see that, oh, we're even getting a different location for the center of everything. The higher you have to look at the resolution you're looking at to see whether you're going to believe what your particles are doing. And the Sioux reference here is of a hybrid approach where you start out with the with the particles and let them move back and forth. But when they diffuse, then you can start converting it into a concentration. But this keeps the high gradients of where things are happening. Now, this would be more comparable if we had a diffusive kick thrown into the models, turbulent kick, which is usually done with particles to give a more realistic representation for things that aren't just in them. Now to the work that I'm close to doing, FECOM, fully comprehensive model. We've got the weather, we've got the boundary conditions, we've got the temperature and salinity all thrown in different bits. And when we do predict the elevation, UV, temperature, salinity, we can then start deriving things pretty directly from the model. We get particle paths and the dye transport that we've shown a little bit already. And we can calculate things like minimum temperature. Salmon blood freezes at minus 0.7, I believe it is. Not a good idea to get below that. They might want to know about that. And low velocity. Fred Page came up with the back of the envelope computation that said if there's a period of time where the velocity falls, let's go back here. Falls below 2 centimeters a second for more than 2 hours, then the salmon go into distress because of lack of oxygen. And from that sort of thing, we can start helping people decide things like where's an optimal farm placement, what are the risks of sea lice and ISA infection, and pesticide transport if they're using pesticides to kill off some of the diseases and sea lice that they find in their models. So the models I'm involved in, and I'm not going to talk mostly about this, the Southwest New Brunswick one, but there's St. Mary's Bay, place in Nova Scotia where they're just starting to look at farms and starting to expand. We take a look at Sherbrooke, Shelburne and Jordan Basin. Susan Haig has a very good report looking at different aspects using pretty much the same grid. That should be being released very shortly, and I think we'll have to look at that carefully when we start looking at doing our own work there. There's a where are we here? Liverpool, that was led by Donghui Zhang, and Donghui was looking at what happens. There already is a cage here by well by this island, and two more are being projected. So we look at how will these interact. Can they be operated independently, or do they have to be very careful in what's going on in each of them and co-manage essentially?
Okay, 2 minutes.
2 minutes? Okay.
2 minutes. Good.
Good luck. Okay, so just two other models that we're looking on, looking at Antigonish Harbor and in Waikagama Bay in Brador, and I'm not going to talk about those. And the open boundary conditions that we're using for the model are from the storm surge model that I've been using, developing, and it gives very good results for the for the elevation. Now, in the most in Southwest New Brunswick, that's where we've got the high resolution. We're down to 5 to 20 meters throughout a lot of the area, just because there are so many farms. And this is just an instantaneous picture. If you look at it a week or a month later, you're going to get a different picture. They're always adding and attracting farms to this area, so we might as well resolve it all at a high resolution. It ends up being very expensive. There are three things we want to, three scenarios we look at that might then go into something like the Markov chain. One is the freshet. What happens in the when you know, in the runoff area, April, May, June, April, May mostly, and then the summer doldrums, and that's what this picture is. It gives you an idea of the resolution we're getting of the temperature. Note it's a very reduced scale, so it's not quite as extreme as it looks, but we are getting good results for that. And the other is in a fall storm, and what you were seeing here was just the black arrows. That was the wind stress. So we take a look at what's happening in the fall period when the storms things really get hairy. I'm going to skip some of the verification, mostly because I'm embarrassed at how little we've done and got more to do. And we'll get into some of the little bit more of the results. We do look at, again, we can track particles going around and the temperature and salinity as they go through. So if people want to put some sort of biological behavior and thing on these things, we can do that pretty easily in these models. The dye that we look at here that is floating around from 5 different areas is cut off at a 1% level. Mitchell O'Flaherty's rule tells me if now it's a different problem. This is being continuously released for 3 weeks in the area. But Mitchell tells me that the if you release the insecticide all at once that you have in the farms, then that you just can't release it to the fraction of a percent is just not enough. It's just too intense. So we do worry about that sort of problem. So well, we can follow things through the depth, through time. The dye at the station was continuously released, and then here's the dye from another station as it shows up at a later time and in different concentrations. And we'll forget about that one, and we'll just go right to the conclusions, just summarizing what's going on. So we are computing the the typical parameters in a hydrodynamic model, and we're deriving the particle path, transport, and diffusion. All of these things seem to be working. We can compute the minimum temperature, prolonged low current speed, which is an O2 deficit problem, and we are getting our insights into the optimal farm placement and density and sea lice, ISA infections, and pesticide transport and diffusion. And if we're lucky, we have time for half a question.
Thank you very much, Dave, for keeping in good time. Yeah, so great. Yeah, questions for Dave. Please put in the question and answer tag.
Are there any plans to add wave in aquacultural applications? None that I know of. They could be important, but so far, no, they are not in the models. And I think that might be a level of detail that we might not believe that it's that accurate if we put it in. It might be sort of like lost in the noise anyway, in that the noise is fairly large.
Okay, if there's no more question, thanks again, Dave.
Thank you.
Bye-bye. And so we'll move on to the next presentation. Jing Tao, she's going to talk about interannual variations of upwelling along the coast of Nova Scotia.
Guoqi, can you see
Yes,
my
I
slide?
can see your presentation. Yeah, good.
Okay, good. Good afternoon, everyone. My name is Jing Tao. I'm working at the DFO. Firstly, I would like to thank my co-author, Yu Hui and Mike. As we know, the Scotian Shelf is the important habitat for the many of the commercial species, which is strongly affected by the Nova Scotia current and the coastal upwelling. The Nova Scotia current brings the nutrient from the Gulf St. Lawrence into the Scotian Shelf. The coastal upwelling also brings the nutrient from the bottom layer into the surface, promote the growth of the phytoplankton and the primary productivity. The Uyama and the Munger 2005 indicate the strength of the vertical mixing during the lifetime of phytoplankton bloom can influence its internal variability in North Atlantic. Many of the previous studies have been examined the upwelling on the Scotian Shelf, but there is no long-term series on the upwelling variation. Also, we found some issues to apply the previous upwelling index on Scotian Shelf. So in this study, we explore use the sea surface temperature from the ocean reanalysis product and the surface wind to develop upwelling indices and to quantify its internal variability on the Scotian Shelf. Here it shows the data we use, including the daily glorious reanalysis temperature product and the CMC satellite SST product from the 1993 to 2022. We also use the Institute SST at the Halifax buoy, which is located near the Halifax. On the left column, it shows the root mean square error correlation and balance between the glorious CMC with the buoy. So we see the glorious SST highly correlated with buoy, and the negative balance is noted on the glorious. Right-hand side column, it shows the time series of the SST from January to December derived from the buoy which shows the black line, and the glorious and CMC, which shows the blue and the green. Here we see the glorious capture certain drops in the SST better than the CMC SST. So here we use the glorious temperature product. Another data we use is ERA5 surface rate. Next is the definition of the upwelling indices. In this study, we use the three components to define the upwelling. First is wind component following the uphammers at 2021, which the wind index is equal to the W is the average wind speed within the study area, which is labeled within the black box. The eta is the wind direction. The 65 is the orientation of the Nova Scotia coastline in the degree. Then we apply the 7 days moving average filter on the wind index. Here, the wind upwelling occur when the wind index larger than the 0. Second component, SST component, is defined as the thermal differences between the coast and the offshore water. The delta SST is equal to the SST offshore, which is defined as 65 kilometer away the coastline. The SST inshore is the like a long cross-shore transit between the coastline and the offshore position. Then we define the upwelling occurred when the delta SST larger than the threshold, where here is equal to the 0.5 southeast degree. Here is give the example of the delta SST patterns. After we apply these two components, we still found the issues to identify the upwelling, since we found some unreal upwelling signals during the winter. So we include the third component. Here we define the TS and the TD, which is the average temperature over the area of interest, is the black box here at the surface and the 55 meter depth. Here, this is the vertical profile of the temperature along this transit. So this criteria is using to define the water stratification and to make sure it is cold water upwelling. So here the third definition is upwelling occurred when the TS larger than the TD over the 0.5 degrees. However, this study, the purpose is to using the sea surface temperature. So we would like to develop a more simpler message. So we try to instead to replace the TD with using the TS. Here is what we did. First, we calculated the differences between the TS and TD larger than the 0.5. Then we found the TS minima in each year during the spring and the fall season. The spring is indicated from January to May. Then the fall is from October to December. Here is give the example of the time series of the minimum TS during the past 30 years. Then we define the threshold as 75 percentile of the TS as the threshold here. In this work, we found the Q75 TS minimum is equal to 3 degree in spring and 7.4 degree in fall. So here we have two different the two definitions. Next, we would like to compare the performance of those two definitions. Here we choose the upwelling area defined using the three components. The left panel is using the component 1, 2, and 3A. The right-hand side is using the 1, 2, and 3B criteria. Here, the x-axis is the year, the y-axis is from the January to the December. So here, generally, we see the second simpler definition produce the similar pattern with the first definition. However, we also found some of the differences in the earlier spring. So in the next following work, we were using the second definition. Before we show more result, we want to know why we need a three component to define the upwelling. So here is the same pattern. The left is upwelling arrow, right-hand side is filtered the wind. The warm color indicates upwelling variable wind. So we see the wind by itself cannot correctly define upwelling. And during the July and August, the strong upwelling activity occurred aligned with the strong upwelling favorable wind. Then here we choose the temporal variation of the upwelling variables we developed using the second definition. On the left-hand side is the upwelling arrow. The bottom is the upwelling intensity, which is calculated by the mean of delta SST. So here is a box plot of the two variables. We see they reach the peak during the July and August, then slightly decrease. In the middle column and the left column shows the error and intensity during spring, which indicates March to May, and for September to November. So we see they both shows the strong seasonal and the interannual variability. Next, we compare the two definitions when they work on the upwelling duration and the community area. Duration is defined as the total date we capture the upwelling signals during the spring and the fall season. So generally, we see the two definitions produce a similar result for the temporal variation. On the bottom two panel, it shows the start date of the upwelling during the spring season we captured using the two definitions. However, we found when we use the second definition, we capture some like the delay, signal delay, and some earlier. So we need some more caution to use the second definition when we work on the start date. The summary, the glorious SST shows a good correlation with buoy data, capturing the certain temperature drops better than the CMC SST. In this work, we use the three components to define upwelling indices, which provide a complementary assessment of the local upwelling process. The upwelling error and intensity both shows the interannual and seasonal variation. Then for the upwelling duration and cumulative errors, the both definition shows a similar result. However, the caution is needed for the start date of upwelling in spring. Overall, we can define the upwelling only use the SST and the wind on the Scotian Shelf. The last, the influence of the temporal variation of upwelling on the phytoplankton group will be investigated in the future. Thank you for your listening. I'm happy to take any question.
Hey, thank you very much, Jim. So now it's the time to ask questions or raise comments. Please put it into question and answer tag. Can you see, Jim? I will read it now. Okay. Is it possible to include index ocean wave features that propagate along the coast that might enhance upwelling locally?
It's possible to include the ocean.
I guess the ocean wave features, it's possible to include ocean wave features that propagate along the coast that might enhance upwelling locally.
Yeah, actually in this work, the purpose is use the sea surface temperature and the wind to develop to define the interannual of the upwelling. So I think the includes the ocean wave will be improved, but it's not the main purpose of this study.
How about maybe the question is there's a slash, so maybe I don't know if that's there's another like factor could be any other like a coastal trapped waves propagating along the coast, not just surface ocean waves.
Sorry, Guoqi, I don't capture your question.
That's my understanding. Maybe not necessarily right, but I think it's because the question has a slash there, so it's the ocean waves and the features, and that propagate along the coast. I thought maybe they also mean not only ocean waves, but also some coastally trapped waves.
Okay.
Propagating along the coast. Well, probably you could answer through the question and answer box, yeah, later on. Yeah.
Okay, thank you.
Yes, also I have a quick question. Have you thought about what could be the reason for interannual variation? Mostly just the wind variation? Oh.
Sorry, they have one question. So why do you have different definition date for spring? Yeah. Actually, the spring we define is from the from the March to the May, but they may have some confused there because we found some like the like issues during the winter, so I just combine that months go to a spring, but the main I can't call it spring. I should call it spring plus winter and the spring. Yeah, sorry, I may do that later. Yeah.
Okay. Yeah. Thanks so much, Jim.
Thank you.
Okay. So now this concludes our second part, and I would like to thank all the speakers for their interesting talks and for all audience the participation. So we will reconvene in 15 to 20 minutes, where we'll have a third part. So see you in 15 minutes. Thank you.